move towards each other, then inflation takes place. Space being created along this direction, and when they get close enough, they collide. When they collide, they heat up the universe. They produce everything. But since in string theory we have strings, so they produce all sorts of strings. Some are tiny strings, like electron, photon, quarks that we know. Some strings are large. Okay, some may stretch across the horizon, stretch across the universe. And so the universe is heat up. That's the beginning of Big Bang, hot Big Bang. And the important thing is that this scenario, one can calculate, looks very good. The key thing is that it produces strings, because everything makes string. Some are small, some are big. The big ones will be what we call cosmic strings. And some of them can stretch across the whole universe. Some of them can be the size of our galaxies. Some, of course, will be tiny, will be particles that make up you and me. Okay. Each of us is made of billions and billions of tiny little strings, what we call quarks, gluons, electrons. So this is the picture that string theory naturally suggests to us how inflation took place. Okay. And of course, when they cool off, they start from structure formations, stars, galaxies, and what we expect that we see outside our own Earth. So, if brain inflation is correct, it will make one prediction, at least, which is naturally testable. That means it will have a lot of big loops, which we call cosmic strings. It's amazing that the prediction of cosmic strings is completely consistent with all the data we know today. And amazingly, that if the prediction is correct, we should be able to detect that in the next 5 to 10 years. Now, there are many ways to study the universe. Okay, so it's not just a theory, but also experiment. For example, Hubble telescope, this is taking data very actively now. This is LIGO, gravitational wave detector, with the 4-kilometer arms, one in Washington State, and one in Louisiana State in US, and then they have one in Europe, and they're building one in Japan, and they're building one in India. So with these large detectors to detect the waves that come from the gravitational theory that Einstein had. And then in South Pole, there are many experiments. Here I only show a few. Okay? That people really build large detectors to search for different things. Ice cube, neutrinos, a lot of experiments there. And people also in high mountains where the atmosphere is dry, telescopes, satellites, many experiments being carried out. So what one said, if we make a prediction, then make sure that somebody can check if you are right or wrong. And that's what we call science. The ultimate test, an idea is correct or not, is the data that people collected from outer space or from the lab. So eternal inflation. While we talk about inflation, there's a possibility where inflation is still happening outside. Okay? Is that true? We don't know. Certainly inflation is not happening here, but it's possibly that in a region we can reach now, inflation is still taking place. That's called eternal inflation. And maybe multiverse. These are questions that we want to ask. So maybe the Big Bang we have is like a single firecracker, okay? Exploded. But maybe that's not quite right. Maybe what's happening is that there's a whole firework show being put on, for example, in festivals, and our universe is just one explosion. Okay? So we have a beginning, but maybe these fireworks have been going on for a long time. So in that sense, that universe may not have a beginning, even though our observable universe seems to have a beginning, because we come from one particular firecracker. We don't know. These are questions we like to know the answer to. Or maybe what we have is not quite right, that brains will collide, but then they can move away from each other and collide bang many times, and that may be what's happening. We don't know. So now we can come back to, does the universe have a beginning? No. Our observable universe, the part that we can see, surely has a beginning. There's no question about it. But what we can see may be only a tiny part of the whole universe. Okay. And if that's the case, then we want to know, does the whole universe have a beginning? Does the multiverse have a beginning? This is a question now we have to be very careful. Okay? If we can never see the other parts of the multiverse of the universe, is this question scientific? By science, we define that you can make some predictions that people can check if it's right or wrong. Okay? If you cannot make such a predictions, or you make predictions that in principle nobody can ever check it, then this is not really science. So maybe this is philosophy. Maybe this is religion. So where's the difference? The difference, I will say, philosophy is something that you have a consistent, logical deduction of what's going to be the case. But there's no way, even in principle, you can think of some experiment to test if you are right or wrong. That's philosophy. Religion is, you don't even have to be self-consistent. Okay? You just have to have faith. And it's amazing is the dividing line between religion and philosophy and science change over time. What used to be religion may later on people find a logical way to understand it, or modify it, or evolve it in a way such that its philosophical opinion is there. And what we consider philosophy at some later time, it turns out that we can think about experiments to do to test it. In fact, the scenarios we talk about how the universe began, for ages people have been arguing as a philosophical question. And it's amazing that over time, we have been able to convert that to scientific questions. And then people will go and do the experiments, observations to test if it's right or wrong. So the dividing line between religion, philosophy, and science is continuously evolving. And our job as scientists is try to put as much of the philosophical questions to see how we can push them to be a scientific question. And this is what people have been doing ages. And what's philosophy? People talk about God, no God, and the Bible will say there's an origin to the universe, Genesis, God created the universe, and people argue right or wrong, and now we believe that the universe have a beginning, so somehow it's created. And in fact, how it's created is a little bit more amazing than the Bible tells us, maybe. Of course, Bible can be sort of explained in an abstract way, or other religion like Buddhism or Muslim. So there's questions we don't know the answer to at this moment, something we do, and yet hopefully maybe we know enough that we can make this more interesting from scientific or philosophical point of view. So what we have learned about nature is that we find that nature can be more amazing than one imagined. I think very few people imagine that the universe, everything comes from nothing. People may think that things pop out created, but now what we find not only matter, but space is created from nothing. And this seems to be what happened in our universe. It's amazing that as we understand better about the universe, and actually other scientific questions, more puzzles and questions keep popping up. So you don't have to be afraid that we will answer all questions. That's not going to be the case. The more you understand something, you can ask a deeper question. You can address a deeper issue. And that actually will, for sure, be the case in science. And what's more exciting is that not only science is exciting by itself, here I just talk about cosmology, but you can talk about life science, you can talk about many other topics. And then a lot of times you ask a pure question out of curiosity, and in answering the question, you will find spin-offs which will transform our society. So I hope that some of you will find science interesting, and you may contribute to society in a way which is unexpected from what we know today. So thanks.
Thank you very much. A very inspiring talk. So I hope you get the message home today. Inflation in physics is good. It creates space, but inflation in the economy. So take good things. Okay, now I'd like to turn the floor over for questions. If you guys have any questions, please raise your hand or.
Y3 is vibrate. How do you know this? What if you like that you have pencil piece vibrate or something like that?
In a string theory, you typically solve the string equations as you solve for violin strings, say. Except the violin string, the ends are clamped down. In string, you have a closed loop, say, like a rubber band. And then they will vibrate, they will oscillate, they rotate, and then you solve for all the solutions, and then that's what string theory is. And in order to satisfy quantum properties, then the string theory have very peculiar properties that we have to have in order to be consistent. And so string theory, to the best we know, is completely consistent with quantum mechanics and with Einstein's theory of relativity. And so, since we believe there's a lot of evidence for both, then we have to combine them in a consistent way, and that leads to string theory. And so the vibration is just property of string theory. That's what strings are. A point particle, there's no just one mode. So that's the difference between string and particle.
Okay, I have a question from the floor also. How can we study dark matter, which is intangible? What kind of experiment do we do to detect?
So that's a very active area of research for people. So we don't know what dark matter is. There's many speculation what dark matter is. Some believe dark matter is a matter very much like us, except that you have no charge, and you will interact with matter we have, but weakly. So that we may be able to produce. So you have proton colliding, and they may produce a pair of dark matter, and that dark matter will behave like missing energy. All people so use LEC to do experiment, or they go underground. They go underground to screen out cosmic rays, and they look at the scattering. That's another way to discover it. People think dark matter may be axion, then they look at the cavity to see if it can trigger transverse electromagnetic modes. So there's many different ways to try to detect different types of dark matter. We don't know which is right, which is wrong. For people who spend their lifetime searching for dark matter, they are taking a gamble of their career. But you require a lot of dedication and trust in what they're doing. So I should point out that interesting in science is that a lot of time you put your life looking for something, and you did not find what you want. But instead, you may discover something even more amazing. And that's essentially the frontier of science, the bonus that you get if you work hard.
What would be the observable predictions due to the existence of cosmic string?
Okay. There's many ways to detect cosmic string. Depends on the property. There's a whole list of possibility. One is lensing. So your cosmic string, if there's something, a galaxy behind it, you'll see double galaxies. One is using pulsar timing, one is gravitational wave, one is B mode in the CFB observation, and so the list goes on. Depends on the property of the cosmic string. Some way is much better than other ways. Again, we don't know which is the best fit.
Okay. There's another interesting question here. I'm not sure if I can interpret it correctly. Since you say that the dark energy converts to all matter during the inflation time, can we say that the dark energy causes inflation or is inflation?
Yes, right. Dark energy is the cause of inflation. So if you have a lot of dark energy, then the universe will expand very fast, but exponentially fast. Okay? And so in the tiny fraction of a second, like 10 to the minus 34 seconds to 10 to the minus 30 seconds, then our tiny universe will grow the size of maybe a good fraction of today's universe. The dark energy density is driving inflation, but the dark energy density stays constant. And then dark energy density times the huge volume give us the energy content. And at the end of inflation, the dark energy is converted to ordinary matter. And that's how our universe heats up. So in the brain collision, you can see the picture. It's very dark, it's dark energy only. And when they collide, sometimes when they annihilate, the brains may annihilate, then all this energy will be converted to hot Big Bang radiation. And as the universe cools, the radiation will become better.
Actually, the last question is my question is, the dark energy is inflaton or not?
Dark energy?
Inflaton is dark energy or not?
No, but it's close. The inflaton is a field that we introduce, and the potential that the inflaton live in, that gives us the dark energy. So that's one more step here. So that in the brain case, the inflaton is the distance between the two brains. And the dark energy is the tension of the brain. So you can see, if you have electron, positron annihilate, then they will disappear, poof, some light. And here also, if your brain, anti-brain, they move towards each other, so the distance between them go to zero, and that means that the inflaton value go to zero. And when they annihilate, all the energy will heat up and convert it to a metal. So that's the difference between the inflaton and the dark energy and what happened.
Okay. As time goes on, the universe is going to cool down to absolute 0 degrees, and you think that the universe will stop expanding then?
The simplest scenario is that as the universe is continuing expanding, the temperature will continue to drop and eventually will approach 0. The universe is dominated by the dark energy, but what happened is the dark energy actually drive the universe to expand faster. That's why last year the Nobel Prize was given for accelerating universe. They discovered that the universe is expanding, but not slowing down. But the expansion is actually accelerating. And that is because of dark energy. So the universe, in fact, is not going to slow down, but actually will even grow faster. And will be very, very dark. This is the most likely scenario as far as we know. But of course, it's possible that at a certain point, the universe will do some quantum tunneling, something else. We don't know that's going to be the case. That's a speculation. And it's unlikely that we'll be able to test that in the near future.
Okay, I have a bit of a technical question here. In particle physics, there is a technique called ADS-CFT correspondence, which models atoms using stack of D3 brains. And are these D3 brains have anything to do with inflation or multiverse?
Yeah. Okay. So this is a technical issue. The ADS-CFT, the ADS stands for anti-de Sitter space. That actually means the vacuum energy is negative. So our universe seems to start with a very large positive dark energy, and then end up today with a very small positive dark energy. But ADS is where the dark energy will be negative. So ADS CFT is very useful in studying string theory and applied it to different areas of physics. It's a very, very deep concept that we probably just barely scratched in understanding what it is. But as far as the universe goes, up to this point, we have not reached ADS. Now it's possible in the future, we may further go down and we may end up with negative CC in ADS. But that's something that we don't know will be the case or not. So at the moment, ADS CFT is a very active area, but the connection to cosmology is not quite there.
This is not a very technical question. It's like, just wondered, so what does it look like at time zero? Is like when you explain what's going on at the following time, but what does it look like?
Okay, that's obviously a very good question. We want to talk about origin of the universe. We could push it back. So we have been pushing all the way to a few minutes. Remember, our universe is 13.7 billion years old. So we push back to a few minutes, we understand that. We push back to a second, we understand that. And then with inflation, we push down back to roughly a trillion of a second. Okay, we push that. But now you want to push to zero. Okay, it's getting harder and harder. So the question is, can we push all the way to zero? Well, we have speculations. People have speculation that the universe have started with, well, I don't even want to call universe. We have no time, no space, and then quantum fluctuation pop out at, say, maybe 10 to the minus 40 seconds, and then that will inflate. That's a simple way to, a simple speculation of what happened. So key is quantum. Okay, classically, you can't have something power nothing. But quantum fluctuation allow you to do that. And so that's the belief. But that is speculation because we don't know how to test them. But even if you don't buy that, we know we start from very little bit, and that little bit grow huge amount. So in 99.99999% of universe is created during the time that we understand what's going on. So it's just tiny little bit there remain mysterious. So there's still work left for young folks.
Okay. Do you think that the string theory is closer to philosophy or religion?
So the key of string theories is that mathematically it's very beautiful. It's a very rich theory, and then that's one reason that people work very hard at it. In order to make that a scientific endeavor, we have to find how to test it. So at least in my talk, I mentioned if they find cosmic strings, that essentially cosmic superstrings, and then they will have particular properties, and that those properties will tell us how our universe is realizing string theory. So that, in a sense, converted to a scientific question. And of course, unfortunately, if they find no cosmic string in the next 10 years, doesn't mean they don't exist. It just means that they're hiding themselves very well.
If the Big Bang starts from a single quantum fluctuation, what prevents further quantum fluctuations in the observable universe to create another one?
Yeah, that's a very good question. There are people who believe there's other fluctuation happen already. So if you look at the cosmic microwave background radiation, there's a cold spot, and people believe that that may be due to a fluctuation and then growth. So people have studied that. So I don't know that fluctuation can happen how often, but typically these kind of quantum fluctuation is very much suppressed. So not having a second one in 13.7 billion years is quite acceptable.
Okay. In my understanding, every particle is come from many different strings, and can we measure the frequency of that string, or can we draw the picture of the string as the periodic wave in 2 dimensions or something like that?
Yeah, so we can talk about the tension of the string, because once you know the tension, then you can calculate the frequency of the function. So the frequency has to do with the size of the loop, say, the length of the string, by what volts you allow. And the tension of the string in the brainwave scenario can depend on warp geometry, where they're sitting in the warp geometry. So it's possible that there's a variety of cosmic strings with different tension and with different properties. They can form junctions. And so you can have many different types of cosmic strings. So the key is to find one, and we can study the properties. So this is in the more realistic scenario, the brain world, where compactification naturally introduces warp flows, and the cosmic string should be sitting in those geometry at the tip of those geometries.
Okay, I've got 2 more questions from the floor. One is that, why are you interested in cosmology, and can we use cosmology in real life? This must come from our high school audience.
Well, I can answer the question maybe. Let me not answer the question, but say it a slightly different way. Okay. Your life is very busy. Okay. A lot of problems come up all the time. You're frustrated. Your friends don't like you. Your mom blame you for something that you didn't do. Okay? Now you sit down and think about, say, the question that I'm trying to think about. Where the universe come from, things like that. That will give you a peace of mind, calm you down very quickly. And in fact, in a very busy time, sometimes I do find that if you think about something, you can play chess. It doesn't have to be this. You can something which you can focus in and put your mind into it for a period of time. It's very, very calming. You should try it. A deep question is very helpful.
Okay, I have one last question from the floor. I just heard the news that neutrino could move even faster than light. Could you comment on that? How could that be?
Yeah. The experiment being done is not a very clean-cut experiment. The way you want to say a neutrino move faster than light is that you should have a beam neutrino, a beam of light, and both propagate, see who travel faster. And that's a clean way to show that neutrino is moving faster or not, or slower than light. What they have done experiment is that they have a beam of neutrino from CERN go through the mountain close to 900 kilometers to Gran Sasso in Italy, go through rocks. And they measure distance, use GPS, which actually don't penetrate the rocks. So they use the uncertainty from GPS, which the estimate can be off easily by a big factor. Now, the same experiment is repeated in MINOS in the US, in Japan, and we have to wait. But all these 3 experiments do not do the real good experiment where there's good control. That is, a beam of neutrino with a beam of light simultaneously produced, and see which one reach the detector. I should give a comment is that the